Hello everyone, this is Tamirasi from T1 section and my teammates are Iqbal and Sricharan. Today, we are going to explain about multiprocessor scheduling. First, let me explain what is multiprocessor scheduling. Multiprocessor scheduling is the process of assigning tasks to multiple CPUs in a system. Unlike uniprocessor scheduling, where we just decide which process runs next, here we also have to decide which processor will execute that process. The main goals of multiprocessor scheduling are efficiency, fairness, and scalability. Types of multiprocessor scheduling. Now, there are mainly two types of multiprocessor scheduling: asymmetric multiprocessing, symmetric multiprocessing. Asymmetric multiprocessing. In asymmetric multiprocessing, one processor acts as the master. This master CPU makes all the scheduling decisions. It controls which task should run and where. The other processors, called as slaves, simply execute the task assigned to them. This approach is simple to design and requires less synchronization between CPUs. However, it has a big drawback. Since all decisions are made by one master, it can become a bottleneck in large systems, leading to underutilization of other processors. Symmetric multiprocessing. In symmetric multiprocessing, all processors are equal. Each processor runs its own scheduler and tasks can be stored in two ways: a common ready queue where all CPUs pick tasks from the same pool, or individual queues where each CPU maintains its own set of tasks. This method provides better scalability and avoids the bottleneck problem as seen in asymmetric systems. However, it requires extra mechanisms for load balancing and task migration so that work is evenly distributed among all processors.
Let's begin with scheduling methods. In a multiprocessing environment, the operating system needs to decide which task runs on which CPU and when. This ensures efficient utilization of all processors and prevents any one CPU from being overloaded. There are three major scheduling methods shown here. Load sharing. This method focuses on balancing the workload among multiple CPUs. Tasks are distributed so that no single processor is overburdened while others stay idle. It's a simple idea, but critical for improving overall system performance and responsiveness. Multi-threaded scheduling. Instead of dealing with entire processes, this method handles threads which are lighter and more flexible. There are two main models: one-to-one model where each user thread maps directly to one kernel thread, and many-to-many model where multiple user threads share fewer kernel threads and the scheduler dynamically decides which maps to which. This allows better CPU utilization, especially when there are many small concurrent tasks. Real-time scheduling. This type of scheduling is used when deadlines are critical, such as in robotics, avionics, or media streaming. Two popular algorithms are rate monotonic scheduling (RMS), which assigns higher priority to tasks with shorter periodic times. And the next one is earliest deadline first (EDS), which dynamically assigns priority to the task whose deadline is the soonest. Real-time scheduling ensures tasks are completed on time rather than simply as fast as possible. Now let's move on to some of the key issues faced in scheduling. Number one is processor affinity. This means that a process tends to stick to the same CPU it ran on previously. Why? Because staying on the same CPU allows the process to reuse the cache memory it built up earlier, reducing overhead from context switching. It's like keeping your work at the same desk instead of moving every time you resume. Synchronization. When multiple processors access shared resources like files or memory, they need synchronization mechanisms such as locks or semaphores. These prevent conflicts, but too much synchronization can slow things down as CPUs might have to wait for one another. Fairness versus performance. Sometimes maximizing system performance can cause starvation, meaning certain processes wait too long or never get CPU time. The challenge is to balance fairness, giving every process a chance, with efficiency, keeping overall performance high. In summary, scheduling in multiprocessor systems is all about making smart decisions, balancing workloads, managing threads, meeting deadlines, and handling trade offs like fairness and synchronization. Understanding these methods and issues helps us design systems that are not only fast but also reliable and predictable.
Let's talk about multiprocess scheduling and some of its real-world examples. Multiprocess scheduling, one of the most important aspects of modern operating system. It's the process that decides which processor runs which tasks and when. In today's world, almost every device, from laptops to smartphones, uses multi-cores. Efficient scheduling ensures all those cores work together smoothly for maximum performance. Real world examples. Let's begin some real world examples of multiprocessor scheduling in popular operating system. Linux. Linux uses something called Completely Fair Scheduler or CFS. The system maintains separate run queues for each CPU core and continuously balance the load across them. The goal is fairness, making sure every process gets a fair share of CPU time without overloading any single core. Windows. Windows uses a priority-based scheduling approach. Here, tasks are given different priorities and the scheduler assigns them to processes accordingly. It also uses process affinity, which keeps specific process tied to certain CPUs to improve cache performance and efficiency. Mac OS and Unix systems. Mac OS and Unix systems uses a hybrid scheduling model. They combine symmetric multiprocess SMPs with affinity models, allowing the OS to efficiently manage multiprocessors while still maintaining flexibility and performance. Together, these examples show how operating systems take different approaches to achieve the same goal: balanced performance and efficient multitasking across multiple CPUs. Now, looking ahead to the future of multiprocess scheduling, it continues to be a pivotal role of computing innovation. With hardware evolving rapidly, more cores, different types of architectures, and complex process, scheduling must also adapt. The main challenge is finding the perfect balance between processor affinity, load distribution, and resource sharing. Getting this right ensures maximum speed and energy efficiency. In future, we will see scheduling systems that uses machine learning and AI to make predictive decisions, adjusting workloads automatically based on real-time usage. This means system will become smarter, faster, and more energy efficient as they learn and adapt. To summarize, optimized scheduling is what powers today's computer innovation, and AI9's algorithms promise even greater efficiency and scalability in the years to come.